Welcome to the lecture module on optics. So far we have described propagation of light in terms of propagating rays, or we described light in terms of ray optics, propagation of light and the various effects that we have studied so far in the earlier lectures in terms of ray optics. But there are several effects such as interference, for example, which is responsible for color of soap films, the colors that we see, different colors in white light that we see of soap films, or what is known as diffraction or polarization. These are some of the effects which cannot be described by ray optics. And then we have to move on to wave optics, as I have discussed in the beginning of this course module, that whenever there are certain areas which can be discussed by one approach, whereas certain aspects can be discussed by another approach. And so, now we move on to wave optics. So, in wave optics we will, so here it is, wave optics, and let me first discuss the various topics that I am going to discuss in this course. So, here, so the various topics which we will see is, first we will begin with Huygens principle, reflection and refraction of plane waves using Huygens principle. Huygens principle is the first time when light propagation was described in terms of waves. Then we move on to interference. First we will discuss a little bit about superposition of light waves, and then describe the Young's interference experiment in detail, the Young's two-hole experiment or Young's double slit experiment will be described in detail. Then we will move on to diffraction, where we will describe single slit diffraction, diffraction by a circular aperture, and we will also discuss the resolving power of optical instruments. And then finally, we will come to the concept of polarization of light, and we will discuss polarization by reflection. There are different ways of obtaining polarized light, but in this course we will discuss polarization by reflection and the Brewster angle. So, before we proceed, we will first discuss some historical milestones which led to the development of wave optics. So, here are some of them which I have listed here. In 1621, Snell gave the Snell's law of refraction, where we knew that it is an empirical relation based on experimental observations. Snell came out with the relation that sin I by sin R is equal to n2 by n1. This we have discussed in detail in the earlier lectures. And then in 1637, the explanation of Snell's law was provided, because Snell's law was an empirical relation based on experimental observation. There was no theoretical support for that. However, in 1637, an explanation of Snell's law was given by Descartes based on a corpuscular model of light, which was later established by Newton, and now it is known as Newton's corpuscular theory. In 1678, Huygens put forward for the first time the wave theory of light, where the propagation of light is described in terms of propagating waves. However, as we will see that Huygens could not answer certain questions such as what kind of waves are these, and therefore, the corpuscular theory prevailed, even though Huygens put forward his wave theory in 1678. For about a century thereafter, the corpuscular theory prevailed. Only in 1801, when Young presented his interference experiment, the two-hole interference experiment, which gave a convincing experimental evidence that light is a wave. Of course, subsequently in 1864, Maxwell put forward the theory of electromagnetic waves, and then it was known that light is an electromagnetic wave, which was subsequently experimentally verified later. So, these are some of the milestones to see, and although the Huygens wave theory is no more used in optics, but the development of wave theory, this was the foundation for the development of wave theory. That is why it is a historical milestone. As an historical milestone, we will first discuss the Huygens principle and Huygens theory of light propagation. So, first recall that we will discuss a little bit about what we know about waves and wave propagation. So, here what I have shown is, recall that a plane wave can be expressed as psi of x t, the disturbance, a wave is a propagating disturbance. So, the psi of x t can be represented as a cos k x minus omega t. This k x minus omega t is called the phase term. So, this is the phase and this is the amplitude, A is the amplitude and k x minus omega t is the phase term, where k is equal to 2 pi by lambda, lambda is the wavelength of the wave and omega is the angular frequency, which is equal to 2 pi into nu. Omega here is the angular frequency equal to 2 pi times nu, where nu is the frequency. At any instant t is equal to t1, the surface of constant phase, it is a plane wave. Why this is called as a plane wave? Because the surface of constant phase, which is called the wave front. A plane wave is a propagating wave with plane wave fronts. Plane wave fronts. Wave front is a surface of constant phase. Therefore, at any instant t is equal to t1, the surface of constant phase is obtained by putting this phase term is equal to constant. So, k x minus omega t1 is equal to constant at an instant when t is equal to t1. Therefore, this part is constant. So, this implies k x is equal to constant or x is equal to constant, because for the given wave k is equal to 2 pi by lambda is a constant and therefore, x equal to constant represents surfaces of constant phase. X equal to constant, if we plot here, that x is equal to constant are planes which are perpendicular to the x axis, and that is why it is a plane wave. So, at t is equal to t1, we have a plane which is here, which is shown here, is the surface of constant phase or the wave front. The wave front is a plane. Now, at a later time, so these are planes perpendicular to the x axis, what is shown here. At a later time t, as t increases, let us say at t is equal to t1 plus delta t, x has to increase. As t increases, x has to increase if this term has to remain constant. So, if we are tracking this wave front, then the wave front is defined by this equal to a constant, some constant value, and therefore, if t increases, x has to increase, which means as t increases, x increases for a given wave front. In other words, the wave will move in the positive x direction. So, this where k is called the propagation constant or the phase constant, because the phase constant multiplied by the distance travelled here would give the propagation phase. It is also at any given instant. So, that is a plane wave propagating in the x direction. What about waves propagating in an arbitrary direction k? So, let us see waves propagating in an arbitrary direction k. So, here I have put waves propagating in an arbitrary direction k, that is k is here. So, x y z axis is shown. Such plane waves can be represented by psi is equal to a cos k dot r minus omega t. Now, k is propagating in an arbitrary direction, which means it will have 3 components. K is a vector with the 3 components k x, k y, k z, and r. So, r is the position vector, which is also given by I x j y plus k z, and k dot r, therefore, is equal to k x x, k dot r, k y y and k z z. So, k dot r is equal to k x x plus k y y plus k z z. If this is a plane wave, this must be constant at a given time. That will give us the wave front, which is a plane. So, therefore, that implies k dot r must be equal to a constant. So, what is k dot r? K dot r is k x x plus k y y plus k z z, which is equal to constant, and we know that this is the equation of a plane. We know that the equation of a plane is a x plus b y plus c z is equal to constant, represents a plane, and therefore, this represents a plane. K here, k dot r is equal to constant, k here is perpendicular to the planes. K dot r is equal to constant implies k is perpendicular to the planes. Its direction represents the direction of propagation of the wave, and the magnitude of this k vector is the same what we have discussed earlier as 2 pi by lambda. The magnitude of the propagation vector is 2 pi by lambda is the propagation constant. So, k, the point to note is the propagation vector k is perpendicular to the wave front, which is true even in the earlier case. We did not show it as a vector because k was along the x direction and the wave was propagating along the x direction, but k in this case is also a vector, but having only one component, and k is perpendicular to the wave front. So, this is the representation of a plane wave propagating in an arbitrary direction. Now, let us look at spherical waves. So, we have seen plane waves propagating along a particular direction and plane waves propagating in an arbitrary direction, and now spherical waves. So, what is a spherical wave? A spherical wave can be represented in this fashion. As before, if we extend the definition of the wave, spherical wave must mean a wave with a wave front which is a sphere. So, the wave fronts must be surface of sphere, and let us see a representation like this, whether it represents surfaces of sphere, is surfaces of spheres or not. So, psi of r is equal to a by r into cos k r minus omega t. Surface of constant phase at any given instant t is equal to t1 is k r is equal to constant. As before, earlier we had k dot r and before that we had k x. Now, we have k r equal to constant, because this part is constant here at a given instant, and this implies that r is a constant. R is equal to constant represents surface of a sphere of radius r. So, schematically shown here that these are, of course, this is a cross section in 2D, but these are r is equal to constant represents a surface of a sphere, and therefore, spherical waves are represented by the phase term which is k r minus omega t. What about the r which is here? So, we will see in a minute. As t increases, therefore, in this expression we see as t increases, r has to increase so that the phase remains constant, because we are tracking a particular wave front. A particular wave front is defined by the phase here equal to a constant, and therefore, as t increases, r increases so that this remains constant for a given wave front, and therefore, the waves as t increases, r increases, which means the wave is expanding, the spheres are expanding outwardly with the propagating time. This is typical of point sources. If I take a point source here, it would give light, it would emit light, a point source at the, then it would emit light in all directions. The wave fronts are in the form of spheres, expanding spheres. So, that is represented by psi of r t is equal to a by r into cos k r minus omega t. We come back to this r now. This r in the denominator takes care of the decrease in intensity. We know that the intensity is equal to psi square, and that means a square by r square, which is proportional to a square by r square, and therefore, we also know that the intensity decreases power or intensity decreases inversely as r square, that is, it is proportional to 1 by r square, and therefore, the amplitude must be proportional to 1 by r. That is why we have a r in the denominator here. So, this is about the spherical wave. With this, we come to Huygens principle now. With these basics, we look at the Huygens principle now, how to propagate waves. So, here is Huygens principle. This is not a specific statement, but it means the essential of Huygens principle, essential aspects of Huygens principle. All points on a wavefront act like point sources that give out secondary wavelets, which propagate outward with the speed of the wave. The wavefront at a later time delta t is given by the surface tangent to these secondary wavelets. We will come back to this statement, we will illustrate what does this mean, and then we will come back to this statement, and then we will understand it fully. So, let us see, let us consider propagation of plane waves using Huygens principle. So, here propagation, so we will come back to this statement after a while. So, propagation of plane waves using Huygens principle. So, let me consider here, consider propagating plane wave. So, here is the wave front. So, the plane waves are coming like this. So, let me show two wave fronts. So, plane waves at a later time. So, plane waves are propagating like this. Now, if this is the wave front at t is equal to t1, the wave front, plane wave front, which is propagating in a particular direction, and therefore, the k vector, the propagation. So, this is, these arrows represent the direction of k, and this could be the x direction. In that case, the wave is represented by a cos k x minus omega t. So, here is the propagating direction. So, according to Huygens principle, every point on the wave front act like source of secondary wavelets, that is, act like point sources of secondary wavelets. So, what I am showing here is point sources. So, point sources of if this is a point source, we know that this will give out spherical waves. So, this will give out spherical waves like this. So, each point source gives out spherical waves like this. So, I am drawing the spherical waves, and therefore, at a time. So, let me bring the statement again. All points on the wavefront, on a wavefront, act like point sources that give out secondary wavelet. Point sources, which means spherical wavelets it will give out, which propagate outward with the speed of the wave, and that means in a time, at a later time t is equal to t1 plus delta t, the spherical waves which are here would have moved. So, the radius of this sphere here, radius of this sphere would be v times delta t. So, this will be equal to the radius which I have shown here of these spheres at a later time delta t would be equal to v times delta t. And the statement says the wave front at a later time delta t is given by the surface tangent to these secondary wavelets, which means if I draw a surface like this, which is tangent to the secondary wavelets, then this would represent the wave front at the time t is equal to t1 plus delta t. Please let me repeat, the wave front is plane at t is equal to t1. According to Huygens principle, every point on the wave front here would act like point sources and give out secondary wavelets. The wavefront at a later time delta t, that is t1 plus delta t, is given by the tangent to these secondary wavelets. So, you have a tangent which is here and they will be propagating outward. So, the wavefronts are propagating outward. We can see here that we could also draw a tangent here just for curiosity, but that means the wavefront at a later time could be on this side, but we know that the wave is propagating in this direction and therefore, Huygens conveniently said that there is no amplitude in any direction except in the direction of propagation. The amplitude is finite only here. So, let me show this slightly bigger. So, here is one of the point sources, that is one of the point sources on the wavelet. So, here is the wavefront on which we have. So, this spherical wave is propagating outwards, but if the wave is propagating in this direction, Huygens said, he assumed, he postulated that the amplitude would be finite only here, that is which is at the point of the tangent, and there is no amplitude anywhere else. This is of course Huygens' assumption there to avoid the issue of backward propagation in this case, and therefore, he said that the amplitude is finite only here in the direction of propagation, and therefore, the new wavefront will be represented by this. So, this will here is the blue line which will represent the new wavefront at a later time t1 plus delta t. If you continue this at a later time t1 plus 2 delta t, then we have to draw spheres of radius equal to v times 2 times delta t, or alternatively you could consider secondary point sources here, point sources on the second wavelet, and draw again spheres like this in the spherical waves coming out of the point sources, and then they are tangent to the tangent to these secondary wavelets would represent the wavefront at a later time. So, this would be the wavefront at a later time t is equal to t1 plus 2 times delta t, and so on. In other words, this represents, this explains the propagation of plane waves in the direction of k with time, evolution of the wave with time. So, we come back once more just to the statement that all points on a wavefront act like point sources that give out secondary wavelets which propagate outward with the speed of the wave. The wavefront at a later time delta t is given by the surface tangent to these secondary wavelets. I suppose it is now clear. So, let me draw the let me put a pre-drawn diagram, the same diagram which I have pre-drawn. So, you can see here just for clarity. So, this was the wavefront at t is equal to t1. At a later time t is equal to t1 plus delta t. So, this I picked up 3 points here. Of course, every point there acts like a point source, but I have just shown 3 points and spherical waves which are emanating from here, and we draw a tangent to all the wavelets which give us the wavefront at a later time delta t, t1 plus delta t. And if you continue, then at a later time t is equal to t1 plus 2 delta t, you get the wavefront here and in the direction of propagation. So, the new wavefront at a later time delta t is the envelope tangent to all the secondary wavelets. This is an important statement which we will apply in the subsequent propagation. And the amplitude of the wave at the tangent only, that is the assumption that that was required for Huygens to show that the wave is propagating only in the forward direction. Now, let us look at propagation of a spherical wave. So, propagation of a spherical wave using Huygens principle. So, as before, so let me take a sphere here. So, approximately, so this is the point source and which has given out a spherical wave front which is propagating outwards, because light is emanated from here, it is a point source and we have just seen that it gives out spherical waves which can be represented as A by R into cos k r minus omega t. So, this is propagation. Now, let us apply Huygens principle. According to Huygens principle, let me use a different color here. So, we have point sources, we consider point sources on this, and then these point sources give out secondary wavelets, this. So, I am showing the forward half, because he has said the wave propagates the secondary wavelets outward in the forward direction, because the k is in this direction, and according to Huygens the amplitude will be present only at the tangent. So, I have drawn here wave fronts, wavelets, these are secondary wavelets, and the new wave front will be a tangent, a surface which will be tangent to all the secondary wavelets, to all the secondary wavelets, and that would be again a sphere. So, if this is a sphere, then this will be a sphere at a later time t 1 plus delta t. So, let me put a pre-drawn diagram which will make it more clear. So, here is the spherical wave. So, the spherical wave at t is equal to t 1 is here, and we have point sources here. So, I have shown here, and the radius here, if it is at a later time delta t, the radius of these spheres here will be equal to v into delta t, where v is the speed of the wave in the medium. So, that is how the spherical waves are propagating outward, and the statement again that the new wave front at a later time is the envelope which is tangent to all the secondary wavelets. So, this is I have drawn them by hand, and here is a diagram we can see which is drawn using a computer. So, we can see that, so this is at a time delta t and this is at a time 2 delta t, and you have wave front which is tangent to all the secondary wavelets. So, plane wave propagation in this direction. So, these are shown as dotted because they are not to be considered in this direction. So, we have in the direction of k, the amplitude of the wave is present only at the tangent, that is Huygens assumption. And therefore, here we can see this is the original wave here, spherical wave, and at a later time delta t we have the new wave which is tangent to all the secondary wavelets. All right. So, propagation is fine. So, this way we are able to, or Huygens was able to explain or describe the propagation of plane waves, spherical waves, or in general propagation of light waves. But do this principle or do Huygens principle or do this way of propagation, does it satisfy the law of reflection and the law of refraction? Because Snell's law was already known, and therefore, does it satisfy the law of reflection and refraction which were already known at that time? So, let us explain the laws of reflection and refraction using Huygens principle as explained by Huygens. So, here is a plane wave incident on a mirror. So, what is being shown is a beam of light which is incident here, and these are plane wave fronts here, and incident on a mirror, plane wave incident on a mirror. PQ is the surface of a mirror. At a certain time t 1, the wave front has just reached here A B. Let me call this is the wave front at a time t 1. Now, this end of the wave front will take some more time to reach the other end. So, if this is delta t, if the time taken is delta t, then this will be equal to V times delta t. The point A, this is the wave front, AB is the wave front, the point A has already touched the mirror, and therefore, light does not propagate beyond the other side, because this is a mirror, it is a reflector, and therefore, the secondary wavelets will start coming out in this direction. So, the secondary wavelets will be emitted in this direction. So, they will start propagating in this direction with increasing time. As this end approaches here, the wavefront which has already reached here creates secondary wavelets, and they start propagating coming out in this direction, because this is a reflector. For example, by the time the wavefront, the point B reaches here, this end of the wavefront here, I have taken 2 points on this wavefront. So, here at approximately 1/3, the separation is approximately 1/3, 2/3 of the total distance, and this point reaches here. By the time the point B of the wavefront, by the time the wavefront reaches here, we see that this will reach here, and as this propagates further, this will start giving out secondary wavelets. So, this starts giving out secondary wavelets, and by the time the wavefront reaches here, this point has reached O2. O2 is another point which will start giving out secondary wavelets. So, this is the secondary wavelet. So, this keeps giving out secondary wavelets, and finally, when this end of the wavefront reaches here, this has already given out secondary wavelets, this has given out secondary wavelet. So, how much time? What would be the radius? For example, this will take, this is, so each segment, the time taken to travel this is delta t by 3, because delta t is the total time taken from B to C for the light wave to travel from B to C. Therefore, the time taken by the wavefront to travel here. So, delta t by 3, this time, the time corresponding to this distance of propagation is also delta t by 3, and this will also be, because I have taken 3. Sometimes you can take only 1 point midpoint or 4 points, whatever, any number of points can be taken. So, I have just taken 3 different points, and therefore, this radius here will be V into delta t by 3, V into delta t by 3 will be the radius of the wavefront which is here, and this will be equal to V times 2 times V into 2 delta t by 3, and this radius here will be equal to delta t is the time taken here, and therefore, that will be equal to V into delta t, and therefore, V into delta t is this distance. So, the radius will be obviously larger. So, we have according to Huygens principle. So, we have shown the wavefronts here of the secondary wavelets. These are the secondary wavelets propagating outward from the points which we have considered. According to Huygens principle, the new wavefront, so we see the statement that we have written that the new wavefront is given by, so the new wavefront will be, the new wavefront at a later time delta t is the envelope tangent to all the secondary wavelets. So, the envelope which is tangent to all the secondary wavelets. So, here is the envelope, I am drawing the envelope, the tangent to all the secondary wavelets is a straight line. So, we can see that it is tangent here, it is tangent here, and it is tangent here. So, this will be the wavefront of the reflected wave, which is a plane, wavefront. Once this is plane wavefront, we know that it will start propagating in this direction with plane waves like this. So, plane waves which are traveling in this direction, which are parallel to this as time progresses. So, I will show a more clearer diagram here. So, this is how I have shown you how to draw the plane wavefront on reflection from a mirror. So, let me show you a pre-drawn figure here. So, we can see here that the 3 points which I had taken, here I have taken only 3 points. In the previous case I had taken 4 points, just to illustrate that there are so many wavefronts and the tangent would give, the tangent to all the wavefronts would represent the wavefront after reflection. So, in this case here I have shown only 3 wavefronts here, 3 points. So, one end, so the end point here, end point, midpoint and this. So, end point, midpoint and here. So, there are only 3 points which are shown here, and you can see the incident wave and the reflected wave. So, BO3 from here to here, BO3 is equal to delta t times V, if delta t is the time for it to travel here, which is also equal to the radius OH of this wavefront, because when this was at B, the point has already touched O1 here. The other end of the wavefront is at O1. Therefore, it immediately starts giving out secondary wavelets, and therefore, this is equal to O1H, which is also equal to O1F here, because this is a sphere. So, O1H or O1F. So, by the time the incident wavefront reaches from B to O3, the explanation is written here, B to O3, the secondary wavelets from O1 reach H, from O2 to the point K, from O2 to the point K here, and so on. And the surface tangent to these wavelets give the reflected wavefront, which is shown here, which is a plane. And therefore, subsequently it will propagate as we have already illustrated. So, this represents reflection by a mirror. But let us see whether this satisfies the law of reflection. So, let me put a better figure now. So, here. So, let us see whether it satisfies the law of reflection. This is the incident wavefront, this is the reflected wavefront. So, now we have seen here AB is the wavefront just before it touches here AB, and this is the reflected wavefront FC. If this is the normal to the mirror and the beam is incident like this, which means this represents the angle of incident I here, then this will be I, because this is 90 degree. So, this angle here is also I, because the whole angle from here to here is 90 minus I. Therefore, this must be I, and this is I. Similarly, if this is R, then this angle has to be R. So, this angle is 90 minus I here, and this angle is R for this triangle here, because this is 90 degree and this angle is R. Therefore, the remaining angle here is 90 minus R, 90 minus R here, and therefore, this angle must be R. So, that is how we have this equal to I and this equal to R. And therefore, in the triangle ABC, sin I, this angle is I, therefore, sin I is equal to BC, that is the opposite, BC divided by AC, hypotenuse here, which is equal to BC is V into delta t, the distance equal to V into delta t, BC equal to V into delta t divided by AC. Similarly, in the triangle AFC, where FC is the reflected wavefront, sin R, this angle sin R is equal to AF divided by AC, AF divided by AC, which is equal to V into delta t by AC. And therefore, it simply means that sin I is equal to sin R, or I is equal to R, which is the law of reflection. So, the law of reflection is satisfied by Huygens construction and propagation using the Huygens principle. Now, let us look at the law of refraction. So, law of reflection, it is satisfied. Now, let us look at law of refraction. So, here it is, refraction at an interface between two transparent media. So, as before, so this time I am not drawing because it is shown here, incident wavefront is here, is coming here, and by the time this travels from here, at this interface the secondary wavelets start coming out. So, the secondary wavelets come out, and when B reaches here, the secondary wavelet reaches here. Note that the refractive index are different N1 and N2. N2 is greater than N1. If N2 is greater than N1, we already know by Snell's law that the ray will bend towards the normal, or the beam will bend towards the normal. So, if it has to bend towards the normal, then if N2 is greater than N1, V2 should be less than V1. If we do not assume V2 less than V1, this distance here AD will be smaller compared to BC here only if we assume that V2 is smaller than V1, because this distance AD is equal to V2 times delta t. Unless this distance is smaller, this wavefront will not bend towards this, and experimentally we already know that if there is an incident ray like this, then it will bend towards the normal if the second medium is of higher refractive index. Therefore, it is essential to assume that V2 is less than V1, and if we assume V2 is less than V1, then this travels a distance AD, and similarly these points will travel the corresponding distance, and the tangent to all the secondary wavelets, this and this here shown, is the wavefront of the refracted wave at this point, and subsequently if this is plane, it will propagate as a plane wave. So, wavefront in the second medium is tangent to all the secondary wavelets, and that is how the wave propagation refraction at an interface between two dielectrics is two media of refractive index N1 and N2 are described using the Huygens principle. So, I keep a more clearer picture of the same picture to show the law of refraction here. So, the law of refraction by Huygens principle. So, see this was the incident wave and wavefront, and then this is the refracted wavefront. So, we can see as before in triangle ABC here, sin I here will be equal to BC by this. So, BC by AC, BC is V1 into delta t. Now, we have two media, this is of refractive index N1 and velocity V1, here it is N2 and V2. So, V1 delta t by AC. In triangle ADC, this triangle in the second medium, sin R, this angle sin R, the refracted angle, this angle is the same as this angle, and therefore, sin R will be equal to AD by AC, which is V2 times delta t by AC. That means, sin I by sin R therefore, will be equal to V1 by V2, which is equal to N2 by N1 by Snell's law, because by Snell's law we know that sin I by sin R is equal to N2 by N1. So, V1 by V2 is equal to N2 by N1. N2 is larger than N1, and therefore, V2 is smaller than V1 if N2 is greater than N1. So, the velocity of light has to be smaller in this medium. Now, Huygens principle successfully explained both the law of reflection and the law of refraction, which were already known during his time. So, that was the plus point. However, Huygens had some difficulty. He could not answer what type of waves are these, because it was known also that these light waves can propagate through vacuum without any medium. Then what type of waves are these? And therefore, the corpuscular theory prevailed, because corpuscular theory had an explanation for what type of waves are these. And therefore, the Huygens theory, although put forward as early as 1637, it could not be accepted for more than a century until 1801, when Thomas Young put forward his famous experiment, which is the double hole experiment or the double slit experiment, to prove that, to convincingly demonstrate that light is a wave. So, we will discuss a little bit more on this. Now, before we go to Thomas Young's experiment, we will see the application of Huygens principle to light passing through apertures. So, let me illustrate light passing through an aperture with by using the Huygens principle. So, what I am discussing now is, see, consider plane waves incident on an aperture. Aperture means a stop which with a certain opening. So, here is a stop, for example, it could be a screen or it could be an opaque plate with an opening here. Plane waves are incident here, plane waves are incident on this aperture. According to Huygens principle, when the plane wave reaches here, so when it has reached here, so let me use the blue color here. We have point sources, the further propagation is discussed using the secondary wavelets. The point sources which are here are blocked by the aperture. So, there is a aperture which is here, so which blocks, it is a finite, it is a plate of finite thickness or some obstacle, and the wavefront which is here start giving secondary wavelets. So, they give out, because we have to see how it will propagate across this, across the aperture. So, this gives out secondary wavelets. So, with the time these secondary wavelets will become larger and larger, and the tangent to all these, so they will further become more and more. So, these each one of the secondary wavelet again acts as point sources, and therefore, these give out wavelets which are like this. And we know that the wavefront at a later time is given by a surface which is tangent. So, let me use the black color to draw the tangent, which is tangent to all the secondary wavelets. So, it looks like this, it is tangent to all the secondary wavelets. But what we have seen is the wavefront now has a curvature, wavefront has a curvature, which means although originally it was propagating like this, now it is the k vector or the propagation direction which is normal to the wavefront also has components in the direction which is away from the original direction here. If we see this more carefully, what it means is that if I plot the wavefront at a later time, it would further become like this. So, what it means is the wave is also propagating in the geometrical shadow of the aperture. What is this word? I have now introduced the word geometrical shadow, geometrical shadow, geometrical shadow. What it means is, if the waves are incident like this, they are propagating in this direction, then because of the aperture there is a shadow, and this wave should have come directly here. As far as if I use the ray theory, for example, rectilinear propagation of light, I should have seen light only coming here, and whatever is the remaining part. So, if I use a different color here, so this portion here is the geometrical shadow of this aperture. There is an aperture here and there is a geometrical shadow, which means as far as the geometry is concerned, the straight rays or the straight lines would go here and here, because it is a plane wave which was incident here. But we see that according to Huygens principle, when we construct the wavefront also propagates into the geometrical shadow. In other words, there is light propagating into the geometrical shadow, which as we will see later is nothing but diffraction. That is the phenomena of diffraction, and therefore, Huygens principle was able to explain diffraction, that is light propagating into geometrical shadow of the apertures. I have some diagrams here which will illustrate it more clearly. So, let me show you some diagrams here. Huygens secondary wavelets at an aperture. So, here, so this is drawn using a computer. So, plane waves are incident here, there is an aperture here. So, we have considered different point sources here and then constructed the secondary wavelets which are spheres originating from the point sources. As you can see, there are no point sources here on the other side because this is an aperture, and therefore, the surface tangent to all the secondary wavelets looks like this. It is somewhat plane here, but it also has curvature in this direction, which means the wave is also propagating into the geometrical shadow. The geometrical shadow would have been here. So, this is the region where the light should have come, but light is also propagating into the geometrical shadow. If you reduce the aperture size, if we reduce, for example, this is the opaque screen, if we reduce the aperture size, then we see that it spreads more. It was almost flat here and a little bit of curvature at the other ends, but now you see that the flat region becomes smaller, it more and more looks like a spherical, it is more moving towards a spherical wave. And if I reduce the aperture further, so let us reduce the aperture further, and we can see that if the aperture size is reduced, the Huygens construction gives us wave fronts which are approaching a spherical wave. Incident wave is a plane wave, and if you reduce it to a very small hole, then we almost have spherical waves which are emanating from the holes. This is contrary to what is expected from the ray theory. So, we see that the wave front is becoming more and more spherical. These observations were made by many scientists and many researchers at that time, and they were getting convinced that light must be a wave, but there was no concrete evidence, there were no experimental evidence with regard to light. Although there were mechanical waves, ocean waves which were seen to exhibit this kind of behavior, but there were no experiments which could prove that light is a wave. So, a further observation here with the two holes, I showed you in the last diagram, there is one pinhole or one small aperture here giving out almost spherical wavelets. And if we, what would happen if there are two holes? Huygens secondary wavelets from two holes in a screen. So, if we draw spheres which are from the two holes, then we observe that there are directions where, so what is shown here, solid line and dashed line. The dashed line represents wave fronts corresponding to troughs. If a sinusoidal wave propagates like this, it has troughs and crests. The amplitude is minimum here and amplitude is maximum here. This corresponds to, so the 2 points are pi difference in phase. The phase difference between the maxima and the minima is pi. So, what is shown here are troughs. So, wave front corresponding to trough and wave front corresponding to crest, which means if I put cos omega t cos k x minus omega t, assume that this is the x direction, then the phase front here corresponds to k x minus omega t equal to a constant. This represents k x minus omega t equal to a constant. The constants are different. If this constant is pi, then this constant is 2 pi. That is the meaning of crest and trough. So, I have shown here the wave fronts corresponding to the minima and maxima. So, correspondingly, if we see the wave fronts here, the dashed line here corresponds to troughs and solid line here, solid curves correspond to crests. So, if you plot these spheres, then there are directions where you see that the solid line meets solid line, the dashed line meets dashed line, solid line meets solid line, dashed line meets dashed line, and so on. Whereas, there are directions where you see that if one, when the two intersection point of the wave fronts, one is a solid and another is a dashed line. Here solid line, dashed line, solid line, dashed line. So, there are directions where the crest due to one overlaps with the trough due to the other, and there are directions along which the crest due to one, that is one hole, one point corresponds to crest due to the other point, which means there must be directions where there are bright light coming, that is the maxima and maxima coinciding, and the minima and the maxima and minima coinciding, which means there would be no light. So, what is expected here is an intensity variation if we keep a screen here. So, Thomas Young gave the double hole experiment in 1801, first with sunlight from a small opening in the roof and then with sodium light. And the wave nature of light was convincingly demonstrated for the first time by Young's experiment, and of course, subsequently he also explained the Newton's rings in 1802 by the wave theory. Now, let me explain a little bit as it apparently the Young's experiment was done the first time when he saw sunlight coming from the roof. So, this is sunlight coming from the roof. He placed an aperture here, he placed a plate which had two holes, two small holes here. So, two small holes. This is sunlight from the roof, sunlight from the roof. Apparently, these are the sequence of events which led to the Young's double hole experiment. And then he could see on a screen placed here in a dark room, sunlight coming from a small aperture in the roof, and there is a plate with two small holes, and he could see a bright fringe here, that is a bright intensity at the center here, and then he could see some colors, and then, so what I am showing here is the intensity variation. I am plotting some intensity variation. We will discuss this in more detail. So, what I have plotted is, this is a screen. On the screen, that is on a, let us say a cardboard sheet or something, that if you plot the intensity, he could see a bright intensity peak, a bright peak at the center here, and then he saw some colors here, and then there is uniform illumination far away from here. This is now very well understood why he saw such a, and we will discuss this in greater detail in the next class, in the next lecture. But this is what Young saw, and then what he did. So, this is first sequence. Then what he did was, he used a spirit lamp. So, spirit lamp here. So, there is a flame which is flame of the spirit lamp, and then he sprinkled NaCl, that is salt, NaCl, he sprinkled NaCl onto the flame of the spirit lamp, which gave the bright yellow color corresponding to bright yellow light corresponding to the sodium here. And now he placed an aperture with the two small holes, very close by two small holes, and on the screen here he could see a large number of bright and dark intensity maxima and minimas, intensity maximas and minimas, due to the bright yellow color of sodium. So, this is a spirit lamp on which he sprinkled salt, and then he saw, due to the bright yellow light, he could see bright and dark fringes here, that is maximas and minimas on a screen placed here. So, this, as we will discuss in more detail in the next lecture, is a convincing evidence that light is a wave. Thank you.